The most common mark for this A-level maths question was 0. Oh dear. In their reports after the exams, the examiners said that this question, question 9, was by far the most challenging on the paper, where the modal mark, that's the most common mark, was 0. And just under half the students scored only 6 points or fewer out of a total of 13 points. Thanks to this person who requested this statics question, you're not the only one, clearly, that finds a way to mess it up. Let's read through the question. It says, a plank, AB, so that's what we've got here, this is the plank, of mass M and length 2A, rests with its end A against a rough vertical wall. So we've got some friction here at the wall. The plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B, and the other end is attached to the wall at C, which is vertically above A. A small block of mass 3m is placed on the plank at the point P, where the distance from A to P is x. The plank is in equilibrium in a vertical plane, which is perpendicular to the wall. The angle between the rope and the plank is alpha, where tan of alpha is 3/4, as shown in the figure 3. The plank is modelled as a uniform rod, the block is modelled as a particle, and the rope is modelled as a light, inextensible string. Using the model, show that the tension in the rope, so that's what we've got here, is given by this. Okay, let's break this problem down. So we've got this plank AB of mass M. So immediately I'm going to put the weight of the plank on the diagram. The weight, W equals mg, so it's going to be mg here, not just m for the force, the weight. And because it's a uniform rod, that means that the centre of mass of this plank, AB, is exactly halfway. So the plank itself is of length 2a, exactly half of that would be of length a. So I put these two lengths a on the diagram to remind me of that. What else? Well, the plank is resting with its end A against a rough vertical wall. So that means that there's going to be a force on the rod due to the wall. In fact, this force is going to be split into two components. A force which is pushing on the rod in this direction, and a force, I'm going to call it friction, acting to oppose the motion of the rod. The rod's wanting to fall this way, so the friction's going to want to oppose that motion. The friction's going to be acting in an upwards direction. So these forces together will form a single force which will be going in this direction. What else? Well, it says the plank is held in a horizontal position by a rope. So there's going to be a force on the plank. So there's going to be a force on the plank. I'm going to call that T for tension, acting in this direction. And because all of my other forces are going up and down and left and right, I'm going to split, in fact, this force into perpendicular components as well. So there's going to be a component here. That's going to be to do with the adjacent and the hypotenuse. So that's going to be T cos alpha, acting in this direction. And there's going to be a component here to do with the opposite in this right angle triangle and the hypotenuse. So it's going to be T sine alpha here, acting in the upwards direction. What else? We've got a small block of mass 3m. It's placed at the plank at the point P. So again, the force, the weight, W, remember W equals mg. Here, the mass is 3m, and we multiply it by g. So we've got 3mg for the force, the weight, not just 3m, be careful. And we're told that this length here is x from A to P. That's already on the diagram for us. Finally, what else have we got? Well, we're told that tan alpha is 3/4. So if we think about a right angle triangle, let's draw one here, where this is my angle alpha. Remember, tan is opposite over adjacent. Using Pythagoras' theorem, you might know that this hypotenuse is of length 5. So that means that sine of alpha, opposite over hypotenuse, would be exactly 3/5. And cosine of alpha, adjacent over hypotenuse, would be exactly 4/5. So how are we going to show that the tension in the rope is given by this? Well, I want to eliminate any forces that I don't know. Notice that in this expression here, we don't have any reference to this force or this force. So if I take moments about this point A, that will eliminate this force and eliminate this force from my equation. So that's why I've chosen to take moments about A. So we know that the clockwise moments, the sum of the clockwise moments, will equal the sum of the anti-clockwise moments. I'm ignoring this T force, that's dealt with the T cos alpha and the T sine alpha, and I can also ignore this T cos alpha force because it's passing through the point A here. So I'm going to ignore that force. So if I deal with my two clockwise forces, I've got mg multiplied by the distance to my pivot point, A, the perpendicular distance there. And then I've got 3mg, the force, multiplied by its perpendicular distance to the pivot, that's x. Next, dealing with this force, we have T sine alpha multiplied by its perpendicular distance to the pivot. That's this entire length here, that's T sine alpha multiplied by 2a. If you get that far, you get your first mark, and you're doing better than most of the candidates that year. Next, we can substitute in sine alpha. Remember, we said sine alpha was exactly 3/5. We get another mark if we get that far. Then we can simplify what we've got on the left-hand side and the right-hand side here. So let's simplify the left-hand side. This and this have mg in common, so I can take that as a common factor. And what have I got left? I've got A plus 3x. And that's what I put in here. On the right-hand side, if I do the number crunching here, 3 times 2 gives me 6, and then I've got my a divided by 5, and the t as well. So that's how I've got to that line. Next, all I need to do is to isolate t. Remember, we're trying to show that the tension, which is what I've called t, is equal to this. So we multiply by 5 and divide by 6a, and you end up with exactly what we wanted for the final mark of part A. Part B. Now we're told that the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2 mg. That's what I called R before, but now I'm going to relabel it as 2 mg because we're now told that it is 2 mg. It says in part B, find x in terms of A. So remember what we just did in part A of this question? We worked out a formula for t here. We might need that later on, so I'm just making a note of it. So what have we already done? We've taken moments about A. Something else that we could do is resolve forces on the rod horizontally. There are only 2 horizontal forces, this one, and they've just told us something about that horizontal force, so probably a good clue there that we should be using that. So, because the rod was in equilibrium, we can say that the rightward forces acting on the rod equal the sum of leftward forces acting on the rod. In other words, in this case, 2 mg equals t cos. Remember, t was what we worked out in part A, so that can go in here. And you remember we also worked out that cos alpha was exactly 4/5. Next, we can do a little bit of cancelling. So notice we can divide by 5 here, just to simplify, and the 4 can cancel with the 6 to give me a 2 and a 3. I'm just simplifying things in the line below. Talking of simplifying, notice that we've got a 2 mg on both sides. So we can divide both sides by 2 mg, and that will simplify the equation further, leaving us with a 1 on the left-hand side. Next, we can eliminate the fraction by multiplying both sides by 3a to get this over here. And then it's just a case of subtracting a to get 2a, dividing by 3, and there we are. We've got x equals 2a over 3. We found x in terms of A. Part C. It says the force exerted on the plank at A by the wall acts in a direction which makes an angle beta with the horizontal. So remember, these 2 forces combine together into a single force which acts diagonally, and they're saying that the angle made with the horizontal, this is the horizontal line, right, is the angle beta. So the angle that this force makes with the horizontal is beta. I've just shown that on the diagram here. Part C. Find the value of tan of beta. So they're not asking me to find beta, they're asking me to find tan of beta. Be careful. So how am I going to do that? Well, one way is to take moments about this point B. The sum of the clockwise moments will be to do with this FR force. I'm ignoring the R force here, and I'm ignoring also this 2 mg force because it would pass through B. So it's only to do with FR there, and that one will be taking us clockwise around B, whereas these other 2 forces would be taking me anti-clockwise around B. Here we go, let's deal with those anti-clockwise forces. Let's start with 3 mg. So we've got 3 mg multiplied by its perpendicular distance to the pivot, which is B. That's distance is going to be 2a minus this length to get this length. So 2a minus x there. Next, let's deal with this mg force. So we've got mg multiplied by its perpendicular distance to the pivot, that's a. And that equals the frictional force here multiplied by its perpendicular distance to the pivot. Remember, that was this length, 2a. If you get that far, you get your first method mark. Next, we can note that we have worked out in part B that x is 2a. So I can replace that into the formula here. Then I can note that every single term in this equation has an a in it. So if I divide everything by a, it will make the formula look a little simpler. And if I do the number crunching here, if I do 2 minus 2/3, that's going to give me 4/3. Notice then that this 3 will then cancel with this 3. So I'll have 4 mg here plus mg, that's 5 mg. If I then divide by 2, I'll get 5 mg over 2 for this frictional force. That's really helpful because now I know an expression for this frictional force, and I also know that this horizontal component of R is 2 mg. So if I consider the right angle triangle that I've got here and think about tan of the angle beta, remember tan is opposite, that's FR, divided by adjacent, that's the 2 mg. So I've got opposite, FR, divided by the adjacent, 2 mg. And I've worked out what FR was. Remember, I've just done that. FR was 5 mg over 2, so that can go in the formula. And if I divide that by the 2 mg, well, the mg's will cancel out, and I'll have 5 over 2 divided by 2, that's 5 over 4 for tan of beta. Don't find out what beta is because the question just asks us for tan of beta, not the angle beta itself. Be careful. Finally, it says, the rope will break if the tension in it exceeds 5. Explain how this will restrict the possible positions of P. Remember, that's where the block of this mass would lie. You must justify your answer carefully. So remember from part A, we had this equation here for T, the tension. That's going to be relevant because it says the rope will break if the tension in it exceeds 5 mg. But we want the rope not to break, right? So for the rope not to break, we'd need the tension not to exceed 5 mg. In other words, the tension to be less than or equal, that would be okay, just about, to 5 mg. we can replace t with the formula we had from part A, and then we can notice that we can cancel the 5mg on both sides, leaving me with a 1 here. Multiply both sides by 6a to get rid of the fraction gives me this. Subtract a to get 5a, and divide by 3. We know that the length x, which remember was to do with the position of p, must be less than 5a over 3 for the rope not to break. So we just need to put that into context into a sentence to finish. For the rope not to break, it means that the block can't be more than this distance, 5 over 3, from A, because that's where we're measuring that distance from A to B from. Did you get it right? Let me know if you got all 13 marks there, and let me know if there are any other topics that you'd like me to go through in a future video.